In this video, I would like to give you an introduction into an exciting topic which has attracted quite some interest in numerical analysis in recent years. It is a fairly young topic, which means it's about 30 years old. The research in that topic started in the 1980s. Since then, it has been recognized that this topic gives an interesting new perspective onto aspects of the numerical analysis of ordinary differential equations, which have traditionally been outside of the scope of traditional numerical analysis. Traditional numerical analysis in this context means 100 or 200 years old. Traditionally, in numerical analysis, we are concerned with error estimates, and this is a purely quantitative notion. We are only interested there in the approximation error. However, in the last 30-40 years, people have begun to recognize that many ordinary differential equations have some innate structure, some innate features in them, which are so fundamental that actually we want to replicate them in our numerical simulations. One such feature is energy conservation, and this video discusses how some numerical methods actually conserve energy at the discrete level. So let me recap the major points. The traditional numerical analysis focuses on the error analysis. We want to develop methods with a low truncation error. And for a long time, that has been considered as the primary purpose of numerical methods for ordinary differential equation. What we see, however, is that these methods tend to diverge over long time scales. For example, in the theory of planetary motion, celestial motion, if you simulate the movement of planets and stars and maybe entire galaxies, then quite quickly you see that over longer timescales, the numerical solution will diverge from the true solution. What people have noticed is that many systems, for example in physics, have additional qualitative properties, such as, for example, energy conservation. And these conservation laws, which are very fundamental for the ordinary differential equations, are unfortunately not replicated by most traditional numerical methods. For example, we are going to see that the Euler method and the implicit Euler method do not conserve energy. And for that reason, people have developed methods which actually do conserve energy. So the practical advantage is that these methods provide better approximation results over longer timescales. And a very important major example for that is the so-called symplectic Euler method. The model problem in our discussion will be the harmonic oscillator, which we've seen earlier a few weeks ago. So let us recall the second order harmonic oscillator equation. We have got a variable p, which depends on time. And the differential equation is p prime prime of t equals minus omega square p of t. P is the position of the harmonic oscillator, and p prime prime is the acceleration of the harmonic oscillator. And since this is a second order equation, we have two initial conditions, one for p itself, p at 0 is equal to p naught, and one for the velocity, p prime at 0 is equal to v naught. Since we already have a very nice framework for first order differential equations, we rewrite this second order harmonic oscillator equation as a system of first order differential equations. So we introduce a new variable v of t for the velocity. So by definition, we have got p prime of t equal v of t, and v prime of t equals minus omega square p of t, with initial conditions p at 0 is equal to p naught and v at 0 is equal to v naught. You've already seen that, and we also remember the energy conservation. We introduce a variable E of t, the energy at time t, and we define E of t as omega square over 2 p of t square plus 1 over 2 v of t square. The energy E of t is the sum of the potential energy at time t plus the kinetic energy at time t. Formally, this quantity depends on time, but actually it's a constant. We can easily check that E prime of t is equal to 0, just plugging in the properties of the differential equation. In particular, if we know the energy at time t equals 0, which is already given by the initial conditions, E at 0 equal omega square by 2 p naught of square plus 1 over 2 v naught square, then we already know that the harmonic oscillator is going to retain that energy throughout the entire time. For that energy term, I would like to introduce also some additional formalism. Namely, we can express this in terms of matrix vector calculations. The energy at time t, E of t, can be written as 1 over 2 times the state vector of the system. First component is p of t and the second component is v of t. Scalar product with the matrix vector product, given as on the slide here. We have got this diagonal square matrix. The first diagonal element is omega square, and the second one is just 1, times again the state variable, p of t, v of t. If you take this matrix vector product and then compute the scalar product, then you will see that we get exactly the formula for the energy that we have on the top of the slide. However, using this matrix language will help us to simplify some proofs. In fact, many numerical methods can be expressed in terms of matrix vector products. For a start, we've got a reference solution to the harmonic oscillator equation. Let's suppose for simplicity that omega is just 1, and that we start the oscillator at position 2 with velocity 2. The solution is a periodic function, a superposition of sine and cosine functions. What we see here is a numerical solution for the problem obtained with a very finely resoluted Euler method. In the left panel, you see the evolution of the position variable over time, where the time in this case goes from 0 up to 20. And in the middle panel, you see the evolution of the velocity variable, as the time goes from t equals 0 up to t equal 20. And finally, in the right panel, you see the trajectory of the position velocity pairs as the time progresses. What we can tell from this picture is that as we plot the solution in the position velocity space, we see that all the configurations that the harmonic oscillator assumes at any time are constrained to a circle. The circle starts at position 2, 2, and then evolves in clockwise order. Also, points on the circle are the position velocity pairs which correspond to the same total energy of the system. Since we have assumed that the frequency parameter omega equals 1, the set here depicted in the right panel actually is a circle. But more generally, if you have different frequency parameters omega, you would see different ellipsoids. Since energy preservation is such a fundamental topic, we would like to replicate this nice feature also in numerical methods. In other words, these numerical methods should have some feature that is similar to energy preservation. So let us have a look what the explicit Euler method looks like for the harmonic oscillator. We have got two variables that we keep track of, and so we have two updates at every step of the explicit Euler method for the harmonic oscillator. Given pk and vk, the position and velocity at time tk, we compute pk plus 1 and vk plus 1 as follows, namely pk plus 1 is equal pk plus h times vk, and vk plus 1 equals vk minus h times omega square pk. And these two equations can be expressed in terms of a matrix vector product. If I put the position and the velocity variable into a two-dimensional vector, then the first two equations here can be expressed as the vector pk plus 1 bk plus 1 equals the matrix vector product, where the matrix has entries 1 h minus h omega square 1 row by row, and the vector is again pk vk. So the iterations of the Euler method just boil down to matrix vector product. The energy at each time step can be computed using any of the two formulas that we had before. The energy at time tk, which we call ek, let ek be the energy at time tk. Then ek equals 1/2 times pkvk times the diagonal matrix omega square and 1 on the diagonal entries times, again, the vector pkvk. And of course, if you compute out this matrix vector product and the scalar product, then what you get is 1/2 omega square pk square plus 1/2 vk square. What we would like to have is that the energy at each time step remains constant. However, that is not true, unfortunately, for the explicit Euler method, and we can check that explicitly. So let ek again be the energy at time tk, and let's also write ek plus 1 for the energy at time tk plus 1. So ek plus 1 is just 1/2 omega square pk plus 1 square plus 1/2 vk plus 1 square. Okay, we would like to know how ek and ek plus 1 compare. And that can be done with some explicit calculations. Unfortunately, the result is not really promising. We have ek plus 1 equal 1/2 pk plus 1 bk plus 1 times, again, this matrix with diagonal entries omega square and 1, and times this vector pk plus 1 bk plus 1. So the first line just uses the definition of the energy at time tk plus 1. Now we already know that pk plus 1 and bk plus 1 can be expressed in terms of the previous iterate, pk vk. So we just substitute in the next line the definition of pk plus 1 bk plus 1. To the right of the diagonal matrix, we now get the matrix 1h minus h omega square 1 times pk vk. And to the left, we get the transpose of this iteration matrix 1 minus h omega square h1. So we've just used definitions and some basic linear algebra here. And the next step is just to compute this expression here. And the way we do that is we compute this matrix product of three matrices in the middle, and that will show us that we get a multiple of the energy at time tk. Okay, so using some straightforward matrix products, I arrive at the formula 1/2 times pkvk scalar product with the following matrix vector product. Namely, the matrix is diagonal with entries omega square plus h square omega to the 4th power. And the next entry is 1 plus omega square h square. And then we multiply that to the vector pkvk. So what we see here is that the matrix in the middle is a multiple of the original diagonal matrix. I can factor out 1 plus omega square h square. And then I get just a multiple of the original energy. So the entire expression equals 1 plus omega square h square times the energy at time tk, ek. What this shows us is that the energy actually increases as we perform iterations of the explicit Euler method. So for that reason, there's an additional artificial influx of energy into the system. As we come back to our harmonic oscillator example, and not only plot the reference solution, but also an approximation using the explicit Euler method, we can confirm the difficulties that the explicit Euler method has with that harmonic oscillator problem. We indeed observe a growth of the energy of the system. The blue curve depicts the reference solution, and the orange curve depicts the solution computed with the explicit Euler method over the interval from 0 to 20 with a step size of 0.04. And what we can see is that the energy of the system indeed increases in that simulation using explicit Euler. Both the amplitude of the position function and the amplitude of the velocity function increase over time. As we now take a look at the right panel and just plot the different pairs of position velocity states which are assumed by the numerical method, we see that the energy increases and that these points go into larger and larger orbit around the origin, so to speak. So that simple experiment corroborates our theoretical observation that the explicit Euler method suffers from an artificial increase in energy that is not a part of the original problem. All right, let's also have a look at the implicit Euler method. In the case of the implicit Euler method, the new iterations, the variables at the next time step, appear on both sides of the equations. For the position and the velocity respectively, you've got the equations pk plus 1 equal pk plus h times vk plus 1 and vk plus 1 equal v minus h times omega square pk plus 1. Now in this particular case, these two equations can be rewritten so that we have an explicit formula for pk plus 1 and vk plus 1 in terms of pk vk. Namely, I pull all the new variables on the left-hand side, so the two equations become pk plus 1 minus h times vk plus 1 equal pk, and vk plus 1 plus h times omega square pk plus 1 equal vk. And what you see here is that on the left-hand side, we actually have got a matrix vector product. We can rewrite these last two pairs of equations in matrix form. So we have the matrix with entries 1 minus h omega square and 1 multiplied with the iterate pk plus 1 vk plus 1 equals pk vk. Okay, this expresses the out iterate in terms of the new iterate with the matrix vector product. Of course, we would like to have it the other way around. And for that reason, we simply multiply both sides of that equation by the inverse of the matrix. Upon doing so, we see that the vector pk plus 1 vk plus 1 equals 1 over 1 plus h square omega square times the matrix 1 h minus h omega square 1 times the vector pk vk. In this example, I've used the particular formula for the inverses of 2 by 2 matrices. Okay, now we can also define the energy, and the energy at each time step is defined in completely the same way as for the explicit Euler method. That is not affected at all by our choice of numerical methods. What is affected, however, of course, is how the energy develops over time. So again, how do the energies compare? If I've got the energy at time step tk and the energy at time tk plus 1, how do they compare? We've already seen that the explicit Euler method leads to an increase of energy, a non-physical, artificial increase in the energy that is only due to the numerical method. Now, if the explicit Euler method leads to an increase in energy, what can we guess, perhaps, for the implicit Euler method? Well, spoiler, it's the other way around. So we can express the energy Ek plus 1 in terms of the old energy Ek. And to do that, we first write down the definition of Ek plus 1. We have 1/2 times pk plus 1 vk plus 1 times this matrix omega square 1, the diagonal matrix, and again the vector pk plus 1 vk plus 1. And that's the first line, the first equation. And to get to the second equation, we only plug in the definition of pk plus 1 and vk plus 1. And from there we proceed similar as for the explicit Euler method. We compute these matrix products in the middle, and doing some simplifications, which I'm not going to read aloud, we finally find that ek plus 1 equals the inverse of 1 plus omega square h square times the energy ek. So here it is the other way around. The energy actually decreases for the implicit Euler method. If the explicit Euler method suffers from an artificial increase of energy, then the implicit Euler method suffers from an artificial decrease of energy. And that is also corroborated by our numerical example here. Again, we have got the reference solution as a blue curve, and the orange curve depicts the numerical approximation obtained by the implicit Euler method with step size 0.04. Everything over the time interval from 0 to 20. And what we can tell here, looking at the position and velocity variables, is that the amplitude of both of these functions decreases over time. That decrease in energy is not part of the physical model. And as we take a look at the right panel, you see that the position-velocity pairs, as time progresses, as we do more and more steps of the implicit Euler method, that these pairs go onto smaller and smaller orbits around the origin. That is not part of any physical system, and it's not desirable in our numerical simulation. So to summarize, both the explicit and the implicit Euler methods suffer from non-preservation of energy. So that doesn't look too good. The explicit and the implicit Euler methods do not preserve the energy of the system. So what are the remedies against that? One possibility is to alternate between the explicit and the implicit Euler method. We've got this term 1 plus omega square h square, and each iteration step of the explicit Euler method increases energy by that factor. The energy gets multiplied with 1 plus omega square h square, whereas on the other hand, the implicit Euler method decreases the energy by multiplication with 1 plus omega square h square to the minus 1. So if we do one step of the explicit Euler method and one step of the implicit Euler method, then we have the same energy as before. Okay, that's one possibility. We could also go the other way around, do one step of the implicit Euler method and then a step of the explicit Euler method. Our theoretical results suggest that alternating between explicit and implicit methods might be a good way to obtain energy preservation on a discrete level. And our numerical results confirm this, at least for the harmonic oscillator. Depicted here are the reference solution for the harmonic oscillator with frequency parameter omega equal 1 and start position 2 and start velocity 2. The blue curve here is the reference solution, and you can tell it's almost identical to the orange curve, which is a solution obtained by alternating between explicit and implicit Euler steps. So as far as we can tell, that method keeps the amplitude of both the position and the velocity constant. We do not see any decrease or increase in energy. And taking a look at the right panel, we see that all the approximations at the different time steps all have the correct energy level. They all lie on the blue curve, which means the total energy of this simulated system is the same energy as for the actual solution. I'd like to draw attention to the fact that the step size for the orange curve is only 0.2, 5 times larger than for the explicit or implicit Euler methods that we have used before. So even with much larger step size, we immediately get an advantage. Technically, we first perform an explicit step with half the step size, and then an implicit step with half the step size for each iteration to obtain the orange curve. Instead, we could also have done first an implicit step followed by an explicit step. The result would have been essentially the same. An alternative, however, is to develop an energy-preserving method. The symplectic Euler method, also known as semi-implicit Euler method, is a numerical method that is very similar to the Euler method, but which provides an energy conservation feature. So in the case of the harmonic oscillator, these two formulas look as follows. The update formula for its position is pk plus 1 equal pk plus hpk, the same as in the explicit Euler method. And for the velocity, we have vk plus 1 equal vk minus omega square h times pk plus 1, the same as for the implicit Euler method. So the update formula for the position is as in the explicit Euler method, and the update formula for the velocity is as in the implicit Euler method, which is the reason people call this semi-implicit. It is also known as symplectic Euler method. Symplectic is a term in differential geometry which does not have a visual meaning. It's just a term that is used there. It's always good to have new terms, no matter where they come from, because then you don't need to use up too much vocabulary. We call it semi-implicit Euler method, or some people call it semi-implicit Euler method, but what is true is actually that this method, that the iteration steps in that method can be computed straightforward. Now, if you take a look at this formula above, we compute pk plus 1 from pk and vk. That's the first step. And then we compute vk plus 1 from pk plus 1 vk, since pk plus 1 has already been computed. That's a straightforward computation. It can also be written in matrix form. Suppose that we already know pk and vk, the approximations of the harmonic oscillator variables at time tk. And then we compute the approximation at time tk plus 1 as follows, namely pk plus 1, vk plus 1 equals the matrix vector product with matrix 1 h minus h omega square, 1 minus h square omega square. Okay, just a matrix vector multiplication at each iteration step. This method does not preserve the actual energy of the harmonic oscillator, but preserves a modified energy. So let's define the energy E tilde at time dk tilde ek as vk square plus omega square times pk square plus omega square times h times vk times pk. So what you see is that this modified energy agrees with the actual energy, except for this last term, plus omega square h vk pk. And then we would like to see how the modified energy ek at time step tk compares with the modified energy ek plus 1 at time tk plus 1. Ideally, it would be preserved. And indeed, this modified energy is preserved. That can be shown with similar techniques that we already used to investigate the energy conservation of the explicit and implicit Euler method. We can again write this modified energy just as the original energy in terms of a scalar product. So the modified energy at time step k equals 1/2 times the vector pk/vk times the matrix vector product with the matrix omega square 1/2 h omega square 1/2 h omega square 1 times again the vector pk/vk. The original physical energy could be written in a similar form. The diagonal elements of the square matrix are again omega square and 1, but this time the off-diagonal elements are not equal to 0. This matrix in the middle is symmetric, And one can show for h small enough that the matrix actually is positive definite. So technically this matrix defines an inner product on the space of two-dimensional vectors. We can show that the modified energy is exactly preserved at every time step of the symplectic Euler method. So let's take the modified energy at time step k plus 1. Okay, that is equal to this scalar product, which we just had on the slide before. And to proceed with the calculations, I simply plug in the definitions of pk plus 1, vk plus 1 in terms of the matrix vector product. Similar as before, I get this long expression with three matrices in the middle that are multiplied. And okay, as I just keep computing this matrix product, I end up with 1/2 times pkvk times the scalar product with omega square 1/2 h omega square 1/2 h omega square 1 times the vector pkvk. And what we recognize now, that term is exactly the definition of the modified energy at time step k. So the modified energy is exactly preserved. In our version of the symplectic Euler method, we first updated the position variable, pk plus 1, and then we used that value to update the velocity variable. However, we can also do the other way around. And that leads to another method that is also known as symplectic Euler method, or semi-implicit Euler method. In that numerical method, the iteration formula is pk plus 1 equal pk plus h times vk plus 1, and vk plus 1 equal vk minus omega square h pk. In this example, the iteration formula for the position is taken from the implicit Euler method, and the iteration formula for the velocity is taken from the explicit Euler method. Remember, it was the other way around for our previous symplectic Euler method. At each iteration step of that method here, we can, for example, first compute the velocity vk plus 1 and use that value to compute pk plus 1. So again, it boils down to a straightforward calculation, and that calculation can be put into matrix form. The vector pk plus 1 vk plus 1 equals the matrix vector product with matrix 1 minus h square omega square h minus h omega square 1 times the vector pk vk. This version of the symplectic Euler method also preserves a modified energy. However, the modified energy is a bit different this time. At time step k, the modified energy equals vk square plus omega square pk square minus omega square h vk pk. In this variant here, the last term has a negative sign, whereas in the previous symplectic Euler method, the last term had a positive sign. Except for such details, in terms of any practical question, the two methods are pretty much equivalent. They will behave differently and produce different approximations, but the overall behavior is completely the same for both of them. Let's see how the symplectic Euler method performs in practice. We have the same harmonic oscillator model problem as before. We start at position 2 and with velocity 2 and consider the time interval from 0 up to 20. The frequency parameter again equals 1. The blue curve again is the reference solution, and the orange curve depicts the symplectic Euler method with a step size 0.2. What these pictures illustrate is that the symplectic Euler method does not preserve exactly the energy of the original system, but preserves a different energy functional that is in some sense close to the original energy functional. Both the position and the velocity functions have a slightly larger amplitude than the reference solution. What is important here is that this amplitude does not increase. And to understand what happens here, it is again helpful to take a look at the right panel. Where we plot the trajectories of the position velocity pairs produced by the symplectic Euler method. What you can see here is that the approximations produced by the symplectic Euler method lie on an ellipsoid around the origin, just like the position velocity pairs for the actual original system. But this ellipsoid is in some sense a perturbation of the original ellipsoid. It looks like somebody took the original ellipsoid of the harmonic oscillator and then applied some minor geometric transformation. The step size here is 0.2, which is fairly coarse, but it's completely sufficient to get a reasonable picture of the original solution. And as we would decrease the step size, the trajectories of the orange curve would smoothly approximate the trajectory of the blue curve. In particular, the orange ellipsoid in the right picture would close in to the blue ellipsoid. And here we see what happens if we use the second variant of the symplectic Euler method. In this case, the amplitude of both the position variable and the velocity variable are slightly smaller than for the reference solution, but they remain constant. And as we depict the trajectory of our approximations in the position velocity plane, we see that they form again an ellipsoidal shape. And whereas the ellipsoidal shape for the first symplectic Euler method was outside of the blue curve and slightly tilted to the left, here we see that the ellipsoidal shape is inside the blue curve and slightly tilted to the right, so to speak. All essential statements are the same. The trajectories of the symplectic Euler method have a very nice geometric interpretation. For any positive h, we consider the function e pv, which is equal v square plus omega square p square plus omega square hpv. The iterations of the symplectic Euler method, pk and vk, can be put into this function and produce then this modified energy. And so we might say that the level sets of the iterates of the symplectic Euler method with regards to the function e are the same. If we start our symplectic Euler method in some level set of the function e, then we are going to stay within the level set. Now, for any such level set, there exists a constant c, such that every single element in the level set satisfies the equation v square plus omega square p square plus omega square hpv equals c. Okay, let's try to understand the level set. So which real numbers p and v satisfy the equation v square plus omega square p square plus omega square hpv equals c? Well, these are all solutions to a quadratic equation in two variables. And what one might know is that equations of that type have been researched for thousands of years. The research dates back at least to ancient Greece. And in this particular case here, provided that h is small enough, this equation describes an ellipsoid centered at the origin 0. And the principal axis and the length of this principal axis are taken from the spectral decomposition of the symmetric matrix that defines the modified energy. Omega square h over 2, omega square h over 2, 1. If we compute the eigendecomposition of that square matrix, then we can tell exactly to which set in R to the 2 the iterates of the symplectic Euler method are confined to. There's an interesting geometric feature here. The principal axis of the blue ellipsoid are just the standard coordinate vectors. standard unit vectors in the x and y direction. The principal axes of the orange ellipsoid, however, are different. In fact, they are the eigenvectors of the matrix of the modified energy functional that we've seen before. Let's do a summary and let's also take a sort of broader perspective. So we've seen that some numerical methods feature something that is akin to energy conservation. Energy conservation is an important feature of many ordinary differential equations and physical models. And so we also would like to replicate that energy conservation structure in our discrete model, in our numerical simulation, so to say. The major application of that, of course, is in physics, where you've got all sorts of conservation laws, and you would like to have them replicated in your numerical analysis. For example, a friend of mine was working on particle detectors, and he told me that he was writing simulation codes for the particle detector, and having things like momentum conservation and energy conservation was actually much more important to him than issues like the local discretization error. So it's safe to say that's an important topic that goes beyond what is typically of interest in computational engineering and computational science. Energy conservation of numerical methods is embedded in this larger picture of structure preserving numerical methods. It's a growing topic in numerical analysis. It has been around since the 1980s, so by comparison, it's still fairly fresh. And I would say a lot of people are interested in embedding more and more qualitative features into their numerical methods rather than just going for low discretization errors. In fact, just ensuring that these qualitative features are preserved already eliminates a lot of possibilities for errors. For example, in the case of a harmonic oscillator, we've seen that the explicit Euler method diverges over time, and you see some energy increase that is completely artificial. If you would use a higher order method, then without taking any precautions, you would also see the same effect. Maybe to a lesser degree, but over time, energy would increase. And if now instead you take an energy preserving method, then you already eliminate many possibilities for errors. Last but not least, the harmonic oscillator is, of course, a very special example. Like whenever physicists are bored to do the harmonic oscillator, it actually comes in different variants. More generally, we might be interested in second-order differential equations of the following form, namely u prime prime of t equal the negative gradient of v evaluated at u of t. Where in that case, v is a potential function. V can be quite nonlinear. For example, in the case of a harmonic oscillator, what you can verify by yourself is I can choose the potential v of u equal 1/2 omega square u. It's just the potential energy. And different physical systems, or perhaps non-physical systems, might be described by a differential equation of that form with, of course, then a different potential. And well, for potentials, and well, for differential equations of that form, we can also develop a theory of symplectic integrators which preserve a certain type of energy. Research in structure preserving methods has close ties with algebra, which might be surprising to some, combinatorics, and also with differential geometry. In fact, the term symplectic, as already mentioned, is taken from the area of differential geometry, where it describes a certain concept. So these structure preserving methods lead you to areas of mathematics which traditionally have not enjoyed much interaction with numerical analysis. However, transgressing such boundaries can lead you to many exciting and interesting results.